We are in the cold neutron guide hall of the Budapest Neutron Center. The neutrons used here are cooled down in a liquid hydrogen tank to 20-30 Kelvin. At this temperature, most of the neutrons will have wavelengths between 3 and 12 angstroms. The yellow submarine SANS instrument uses these cold neutrons to study the nanostructure of the materials. The lifetime of the neutrons is about 15 minutes and their velocity is around 1000 meters per second. They travel to the instrument through a 25-meter-long neutron guide made of nickel-titanium-coated supermirrors. Their low energies or high wavelengths and their lack of charge allow them to penetrate deeply inside the matter. The proper wavelength or proper speed neutrons are selected by a velocity selector located in the reactor hole. The monochromatized neutron beam passes through a collimator to finally reach the sample.
Neutrons that reach the sample scatter on the atomic nuclei in the sample. Those neutrons which are scattered in the forward direction, that is, in angles smaller than 10 degrees, are detected by a 1 square meter area detector. It is placed inside the evacuated chamber of the yellow submarine. In general, neutrons can gain or lose energy during the scattering. In the SANS method, such energy change is not considered, and only the elastic scattering is analyzed, assuming that the scattered neutron does not change speed and energy. After detecting the scattered neutrons, a longer process of data treatment and analysis follows. At the end, the experimentally measured scattered neutron intensity data are plotted in conventional XY graphs as intensity as a function of the scattering angle. Further analysis usually consists of mathematical model fitting of the intensity curve. It gives important and interesting information about the nanostructure of the studied material.
There is no need of special sample preparation. The solid samples are simply placed into the neutron beam. For the liquid samples, we use quartz cuvettes of diverse sizes. Powder samples can also be filled into quartz cuvettes or aluminum holders. It is important to note that the quartz, glass, and aluminum holders are transparent to neutrons. In the most common setup, up to 10 samples can be placed into a sample changer, which can be heated or cooled from 10 to 80 Celsius degrees. An electromagnet of 8 Tesla magnetic field can also be used for the study of the magnetic behavior of the material.
The main condition that needs to be fulfilled for SANS is that the material must be heterogeneous on the length scale from 1 to 500 nanometer. Such heterogeneities can be, for example, nanoparticles, nano or micropores, nano-sized precipitates, micelles, polymers, macromolecules, membranes. Another important criterion is the contrast. The scattering length density of one component of the sample must differ from that of the surrounding.
Let us give some examples. Recently, the nanostructure of steels produced by the rolling with shear has been studied and compared to steels produced by the standard technology. The significant nanostructural difference between the prepared samples was observed in our experiments, and this could explain the advantages of the rolling with shear technology, where besides the nucleation, the healing of the nanovoids is also taking place. SANS and neutron scattering in general, being a non-destructive method, is exceedingly popular for archaeological investigations. For example, from the change of the microstructure, the firing temperature can be revealed, distinction between different producing techniques of old ceramics can be done. Porous materials such as silica aerogels and aerogels, polyurethane, are used in pharmacology as drug delivery systems or transmembrane carriers. The study of their nanostructure, especially of their behavior in water, contributes to the understanding of how they can be fine-tuned for a proper drug release.
The neutrons are scattered from the nuclei. Therefore, they are sensitive to the particular isotopes of the elements. We can replace the hydrogen atom by its isotope, the deuterium, which is called contrast variation method. In this way, we can highlight or hide various parts of the structure. Doing several such measurements, we get detailed information on multi-component systems. In colloidal science, such examples can be various hollow or core shell nanoparticles, or block-copolymer micelles, or biomembranes. In summary, this technique can be used in various fields of physics, chemistry, and materials science. Nanostructure of metals used in industry, porous materials, gels used in medication, building materials, archaeological ceramics, biology-related samples such as proteins, membranes, micelles can be studied. By small-angle scattering, we obtain information about the morphology of the materials on the nanometer length scales. Main parameters of the structure, such as the size, shape, interactions, morphology of the pores and interfaces, can be characterized with a very good precision.
The biggest advantage of the SANS and of the neutron methods in general is its non-destructivity. In addition, the experiment is typically easy to perform. No special sample preparation is needed, except in certain cases, the sample thickness should be limited to avoid high absorption or multiple scattering. The maximum sample thickness can vary between several micrometers and several millimeters, depending on the material. The typical sample size is 1 centimeter in diameter. In the measurement, we obtain averaged information from the sample, averaged to the whole in-beam volume, which is an advantage compared to other surface-sensitive techniques such as electron microscopy. In most of the cases, SANS can complement X-ray scattering methods, but also other nanostructure characterizing methods, like electron microscopy and others. Most of the samples do not get activated. They can be taken by hand immediately after the experiment.